his research describes efficient methods for reasoning about structured models. And his work in random perturbation was presented as a best paper shortlist in ICML 2012, and also in the best paper track in AAAI 2012. He wrote a book about perturbation methods and the reference of statistics and minimization, published by MIT Press. And Tamir's research also includes the primal-dual norm product belief propagation algorithm, which received the best paper award at UAI in 2008. Today he's going to be talking about learning by propagating gradients through Gumbel-Argmax models. So let's thank him.
Well, thank you very much for the warm welcome and the presentation. Yeah, I'm speechless. Anyways, it's a technical topic on something I'm extremely excited about. We'll talk about variational base and with discrete decisions. But what I want to present and think while presenting, and I'll present other works that are related to this, is the pipeline that I think about machine learning when doing research these days. And basically, the first step is the data encoding. And what was feature extraction like 10 years ago. When you work on the data, you make many convolutional operations on it, and then you actually massage the data enough so you can feed it to a machine. And then there is usually a reasoning step over this data. And it's not apparent in convolutional neural networks, but for example, attention models, you see a reasoning step. In variational autoencoders, will show a reasoning step. And in many ways, we want to put some cognition into the machine in order to make the machine work in a way that we understand better as human, because I strongly believe that machines and people in a way will interact closely in the future. If you think, I guess the long-term goal, if you think of a physician trying to cure cancer, they are already getting, and they will get much more notions from the machine on where to look, what to do, and they need interpretations so they can actually understand the machine decisions better. And it really boils down to few discrete choices that they need to look at and explore and sample and understand the uncertainty of a procedure. And after seeing all these options, usually the machine is doing a decisioning phase, right? So it has all the information, explains that it needed the cognition that it looked at, and now there should be some decision to put on top of it. So I'll present a few thoughts in different aspects of machine learning with the same thing. First thing will be generative learning, and this is actually motivated by my kid. I have like this wonderful kid, I adore him. And many of the pictures that I take, he doesn't smile. Like he has this cutest smile, but like he's serious. And I don't want to actually change the bit, like take the same picture and change the bit a bit. Just change the bit to say smile and things like that. So we want to have, in a generative learning, some discrete process to say what will be the characteristics of the image that we want to have. And here, just samples, the characteristics that we have are male, female, smiling, not smiling, glasses, no glasses, right? So this is basically like just a set of discrete choices that we can have and then generate the image from it. We also have some thoughts closely related to the Topcase work that came out from this lab a few months ago and got the best paper award of ICML. We have a synthetic work, right? Just going into rooms, open doors, pick a prize, and there we have a sequence of decisions that we need to make of what will be the trajectory that the robot is making, right? And all the time there are different choices, and you need to choose the actual trajectory, the best trajectory when the environment changes all the time, right? So again, we have some discrete choices. This is called policy, and we need to make sure, like, we need to learn from this policy in order to optimize the reward. Another thing that we are working on is in supervised learning, is we are trying to learn a parse tree, and this is only one example that we have, it's not our motivating example. Our motivating example is actually machine translation. When you get a sentence and there are many translations that are possible from the sentence, but effectively at the end you need to present a final translation. What we are doing here are dependency parsers, and then you can connect each word to its dependent word in order to show connections in the sentence. And you can make these dependencies in many, many ways, right? So we want to sample, so we want to learn some representation of the graph, of the connections between the words, and then we want to sample, and we are sampling about 100 dependency parsers, and on top of that we want to make a decisioning, now seeing all the 100 dependency parsers, what will be the best parse. So this is something we see throughout machine learning these days. So this data massage, decisioning, and then data massage, cognition, and then decisioning. In this talk, I will focus on variational base. And basically, this is, again, something originated from this lab a few years ago, inspiring work on how to actually encode and decode data if you want to generate continuous data. So basically, what we have is some input image, and we want to encode the image into a latent space, which usually is smaller dimension that somehow controls the variability of the image, the light in the image, and things like that. And then we want to decode the image back. And we do it in a generative way. So what we want to do is to learn the parameters of the encoder and the decoder in order to maximize the likelihood of the generated image, right? In a way. So basically, this thing exists in generative learning, and the objective that we are looking at is called the elbow objective, or expectation minimization. It's pretty much the same thing. So we want to maximize or minimize the negative log likelihood loss, and we do that with an auxiliary distribution, which we see Q. This is the distribution that encodes the input into the latent space, and when we sample from this distribution, we want to see how good we decode, after we sample from the latent space, how good we decode the image itself back from Z. So this is, as you see, the P theta of X given Z, is like the best way to decode from the latent space the image itself. In order to balance everything, we always need some regularization, which is how far we go when we optimize, how our derived posterior, how is our probability over the latent space that we learn in the encoding is far from when we started, from the prior distribution that doesn't look at any information. Okay. Questions? How is this equation is known? Who saw this equation for the first time? It will help me to know like how to explain stuff. Everybody saw it. Perfect. Okay, so variational autoencoders. The work of Dirk Kingman, Max Welling, and also Razan and Shakir actually focused on exponential families but continuous distributions. When in continuous distribution, it's very easy to propagate gradients throughout the decoder and the encoder. We are also looking in this work on exponential families, but the thing is we are working over discrete latent space. And discrete latent space, you just sum, and which is good. You don't use integral, you can understand what you get, but it's also bad because the network you should get is a bit weird network, right? The fact that we sum means that in order to compute, we don't have a decoder and then an encoder. We need to sum the softmax that gets out of the encoder with all possible decoder values. Right? So this is how it should be computed, which is nice. Like you can program it, but the thing is, well, it doesn't scale well with deep learning. In deep learning, what we want to do, we want to learn everything end to end, right? And if you just sum, you get a different gradient for the encoder and different gradient for the decoder, and it will not flow nicely in the network, and it will be just harder to learn. So what we want to do is take the discrete setting and make it look more or less like the continuous setting, where everything can flow in one pass. To do that, we use, now it's quite standard, which is fun. We use extreme value statistics to represent discrete distributions as continuous random variables, in a way, with some discretization. It's called the Gumbel distribution, which is pretty much similar to the Gaussian distribution. You can see the Gumbel distribution is the green one. It's almost symmetric. It really looks like a Gaussian distribution. It doesn't decay well enough on the positive side as Gaussian. It decays like the Laplace distribution, but hey, nobody is perfect. But the good thing is, you can sample from the Gibbs distribution, from the discrete distribution. You can get the e to the power of phi by sampling Gumbel noise, Gumbel perturbation, and check how much the best outcome is stable to this Gumbel perturbation, right? So you have features, and you have the phi, the energy function, and you know what is the best assignment for this energy function. What will be the z, the discrete random variable, that will score the highest for phi. If you want to measure this stability, like how much you can change phi in order to keep z to be the best outcome, this is exactly measured by the Gibbs distribution. So the stability of the Argmax solution to random shifts is actually measured by the Gibbs distribution. And this very nice behavior comes from extreme value statistics, was understood by Fisher already, like everything in statistics, already in the 1920s, but Julius Gumbel made a huge effort in the early 50s to formulate everything, and they honored him by that. This distribution and extreme value statistics, and the fact that we need to choose, it's something that goes beyond machine learning. Actually, it was well developed in choice theory in economics. The Nobel Prize was for that. It's a very powerful tool that we can see across fields. But basically what we want to do is to take the discrete choice and make it a continuous choice. Now, the sampling that we have are no longer discrete samples of z from the Gibbs distribution. The samples are continuous random variables, that the Gumbel random variable. And the fact that we have continuous random variables now will help us in few slides to make gradients flow through the network. So this theorem already helps us to create this structure of this forward pass, like just make the network as we need to have in deep learning. We have the encoder to encode the input into the latent space, and then we inject some Gumbel perturbation, just Gumbel random noise, into the encoder function, and take the Argmax, which is a one-hot representation of a vector. It's the same thing. Once we have this Argmax, we feed it into the decoder, and then push forward the information. So we can get everything in one pass. Right? The feed-forward pass, just computing the function. And this is very nice to work with the deep learning. This is the way to work with it. So just to make sure like we have all, so the Gumbel perturbation allows us to do the parameterization we like so much, right? To work with networks as an end-to-end learning. So if previously in unbiased setting we needed to use encoder, many decoders, and multiply and sum to get softmax and sum everything, now we can have everything in one pass. Well, what's the bad thing about it? It's very hard to backpropagate. And just computing the gradients of this network it's brutal, because the Argmax function, which is the one-hot function, and one-hot I didn't explain, I should have. The one-hot function is a function that has 1 in the Argmax and 0 everywhere else, right? And this function is actually not differentiable. It it has a gradient, which is infinite in few places, and beyond that, the gradient is 0 everywhere. So it's 0 almost everywhere. We cannot just do back propagation through it. And this is the main problem. So one thing we can do is instead of the argmax that just disappeared, we can put a softmax. And the softmax function is a differentiable function, which is great. And this was done like a couple of years ago, both by Chris Madison and colleagues and Eric Jung and colleagues. And it's called the Gumbel softmax. There are good things about the Gumbel softmax. It's very easily applicable because you just use networks as you use. You put some random perturbations outside of the network and run everything as you always used to. Well, the bad thing about the Gumbel softmax is, on the one hand, it changes completely the function, the optimization function. So now it's fine. It propagates exact gradients on an approximated objective, and this approximate objective is not really clear, like what it does and how is it far from the original objective. And in our work, we want to work on the exact objective, but instead do approximated gradients because, and we'll see it from the experiments, working with approximated gradients is not a bad thing because you actually manage to explore the space, but working with the right objective is I think it's pretty important. So the main theorem of this talk is how to propagate gradients through such a network. Okay? And I'll try to do it so because I think the proof is actually simple. And I think it's like somehow fun. And basically what we need to do, so we have a gradient over the parameters of the encoder. These are W's. And then we have expectation over gamma because we sample gammas all the time. These are the Gumbel distributions. And we have our decoder over the encoder output, the 1 hot. And Z is the 1 hot that gets out of the encoder. So basically, when we do a gradient of expectation, we expect to see Markov chain Monte Carlo or some sort of sampling, reinforce, some sort of sampling. What we are trying to do, and it's not only this work, it's what like few works that I'm having, is instead of doing sampling, just do optimization. Implicitly sample through optimization. And in this way, you'll make the sampling much more efficient. And in this case, instead of just sampling and do MCMC on top of it, what we'll do is just get 2 types of optimization. You can see one is the Z of the encoder phi and the Gumbel perturbation gamma. And the other is Z with this epsilon theta, which is not clear why I'm doing that, but you'll see it. This is in order to push some signal of the decoder because I want to optimize the decoder eventually. Okay? So this is basically what I'm trying to do. I'm trying to get the gradient of expectation, but instead of working with expectations, I'll try to work with optimization instead. So this like magical formula, why is it true and why it's not like so hard? So basically, and I should have broken these slides to 1, 2, 3, 4 different slides, not to scare everybody. It's not that scary. I know it looks scary. I try to look at it with you and walk you through, and then I'll try to ask some questions so you'll have more time on the slide to look at it. I think the most important theoretical component we build for this work is the function G. It's a generating function. Usually we are used to look at moment generating function or probability generating function. What we have here is, in a way, a prediction generating function. Because the gradient, the prediction itself, which is the Argmax, appear in the gradient of this function. This happens because the gradient of the max function is the Argmax function. Okay? So when we differentiate the max function, we effectively work with the Argmax function, and then we get everything we want. So when looking at G, the first thing we notice that this is a smooth function, so it has gradient and Hessians and everything. On the second look, we'll see that what we want to prove, which are these 2 sides of the equations, actually appear in the Hessian of this function. Okay? And effectively, the theorem says is that the Hessian is symmetric. And that's the whole proof. Like looking at the Hessian of this prediction generating function, and since the Hessian is symmetric, I know that everything will work out. So the only thing we need to make sure is that both sides of the equations are represented by the Hessian of this prediction generating function. So on the one hand, if I differentiate with respect to epsilon, what will I get? I'll need to differentiate through the integral, which is fine. Expectation is integral. It's the same thing. So that's fine. The gradient pushes from the integral inside. Then I need to integrate over the max function, right? And this, I'll get the Argmax function. And the Argmax now, for everything that is within the max. So it's the Argmax of epsilon theta plus phi plus gamma. And then I need to differentiate with respect to epsilon. I have epsilon theta, right? So the chain rule says that I need to differentiate epsilon theta with respect to epsilon. I only get theta. So what I'll get is theta x of z, of the Argmax of what I have there. Since epsilon should be 0, it drops out. So it's really what I need. This is the gradient that I need. And if I look at and now if I differentiate with respect to epsilon, so take the second derivative now, with respect to w, I'll get the derivative with respect to w of what I need. So this is nice. Everything appears, so the left-hand side of this equation appear on the Hessian at the point epsilon is 0 when I first differentiate with epsilon, then differentiate with w. If I do the other side, first differentiate with w, first differentiate with w, I'll work immediately on the gradients of the encoder. Right? The same thing. I'll differentiate through the expectation, through the max, I'll get the Argmax, and now I'll differentiate through the encoder, and then I have the gradient of the encoder. Okay? And the Argmax will be z at the point of epsilon theta plus phi plus gamma, because this is the Argmax. And now differentiating with respect to epsilon, this is the second, this is just the definition of derivative, right? And this, what I'll have is the difference between the two derivatives of the encoder. So I want to advance in the direction of the derivative of the encoder, but only in places where the prediction changes, right? Which prediction changes? When I insert some information from the decoder. Okay? And if I insert some information from the encoder, it makes sure that I go towards, from the decoder, it goes toward the area of the better prediction of the decoder and goes away from the area that the decoder doesn't predict well. Right? So I'm just looking at two gradients and take the difference of both of them. Well, the nice thing, this is the most heavy slide, so I will have 2 more minutes on it. Questions? Europe. Well, the Hessian is symmetric. Like, no, it's like both W and epsilon are defined everywhere, which is nice. They are not conditioned or something. If it would have been conditioned, it wouldn't be true. I guess I would have need to take the Hessian of the space itself as well. Yeah.
So do you compute this term on the right-hand side of the theorem analytically? Can you do that?
No, epsilon is 0.1.
Oh, so you use it like a finite difference?
Yeah.
There's still a bias left.
It is. It's a biased gradient towards the true objective. So since we still maintain the right objective, although the gradient is biased, it goes to the right objective. And when we see the Gumbel softmax, it's an unbiased gradient towards the biased objective in a way. Right? So you see a difference in the way they converge. I'll show it. And this is something, and Alex, I have a slide on it. Like, there's something weird going on. I'll talk about it more. Right, 2 minutes. Okay, so there is something interesting here. You can see that I'm working with two predictions. One is decoder perturb prediction, and one is only encoder-based prediction. Basically, I don't need the encoder-based prediction. I can see since I have a full probability on it, the gradient itself is 0 of what I have there. This is the score function, and it comes from, I guess, in force we can see it everywhere. This is actually a built-in control variate ingredient because I can live without it. It's the same type of gradient when I take an expectation, but what I get is this gradient is non-zero only in the boundary of decision, which is really nice. Like, it really decreases the variance of this estimate. And if I compare it to the variance of the Gumbel softmax, which is not a fair comparison because we are checking different things. Our variance comes from this epsilon, and their variance comes from the temperature that they are using because they can control the temperature. These are different things, and I'm aware of that. And yet, if I just compare these two different things, we can see that this built-in control variate element is quite powerful. And we've seen it. So sometimes we work with it, sometimes we work without it. We see that it goes to the same place all the time, but it's really nice to work with it when possible. So let's remind ourselves which algorithm we have so we can actually compare to see what's going on. So we have the unbiased gradient, like the right objective that we can work with, and we compare to it. So we have an encoder, softmax, many decoders, and make a sum over them. This, in a way, an attention mechanism. Any attention mechanism works this way. We have the Gumbel-Argmax and the Gumbel softmax, right? So we have 3 types of algorithms, and we want to compare them. What we would have expected, and it's not the case, we would have expected that the top one will be the best and probably the slowest. And, well, we hope that the Argmax will be better than the softmax, otherwise we wouldn't be able to publish. So this is more or less what we tried. And it turned out to be a bit different. Well, the Argmax is better than the softmax, otherwise we wouldn't be able to publish. But what we see, well, we see that the blue, which is the unbiased, well, it's good, right? You can see that for 10 discrete latents case, it goes the same as the Argmax, which makes sense because both of them optimize the same objective. It's a bit slower. You can see it on Omniglot, which turned out to be a weird data set, that it goes in steps, don't know why, but effectively it goes to the right place. And we also checked everything in wall clock time because, well, we need to do the Argmax when Gumbel softmax have a very easy backward pass, and we need to do the Argmax every time, and because we have 2 optimizations to work with. And we did it in the batch operation, so it turned out to be not that bad. So in wall clock time, you can see we are like pretty much close to the Gumbel softmax. And we can see, as I said, the unbiased, it takes time for the unbiased. It turned out to be more interesting when we increase the latent space. Let's start talking about the unbiased. You can see how bad it is. And it's not clear why it's so bad. It might have more steps in order to go to the right direction. And it might not. We need to remember we are optimizing non-convex functions. So it's not clear that one algorithm should be the same as other or different than other. Which algorithm chooses better local minima? I don't know. What I do know is that we are using stochastic gradient descent with biased gradient. So we actually shoot directly towards prediction, while the unbiased take the right gradient in a way. And it might not do the right exploration in a way. It's not aggressive enough in the beginning of the exploration, and this might explain the steps, and this might explain the slow convergence. It's still not clear what's going on, but I think there is some evidence, yet another evidence of the importance of stochastic gradient descent and the importance of going a bit aggressively towards the best prediction, because you don't really need, especially in the beginning, the right gradient, right? You just need to go in a way to the direction that you think will be most fruitful. In a way, I'm just half joking, pretty much like research, right? You need to, in a way, bet on the best direction you can get in order to get the best thing. It might, yeah, I'm half joking. Another thing that is surprising is the Gumbel softmax, the gap between the Argmax and the softmax, right? Because both of them, as Max said, are bias gradients. We have the bias in the epsilon, they have the bias in the softmax. And yet, we get, and this is consistent, better local minima. And I think it's, since we are shooting towards the right objective, and they're shooting towards an approximate objective that it's not really clear. We also integrate the KL divergence in a seamless way in our framework, because we have, again, the Gibbs distribution, their KL divergence is only an approximation. So they really shoot for a different objective in a way. And we can see in the wall clock time, it's pretty much comparable. It's not that of a big difference. I guess it's twice as long compared to Gumbel softmax, maybe 3 times as long as Gumbel softmax. So like, it might be worth the effort. But think about it, we didn't even started exploring the main motivation of generating images with many attributes, right? And the problem in this case is structured setting, high-dimensional setting. How can we do that? So the encoder cannot output exponentially many assignments, because just impossible. So we usually work with decomposed encoder, which is sum of, say, if we have n random variables, sum of n encoders, which makes sense. And if we do that, we can work with low-dimensional Gumbel perturbation. So for Gumbel perturbation for each dimension independently, and then at least the best z from the encoder can be inferred quite efficiently. Which is like, it was initial thought, and then we realized, oh, there is a problem with the decoder. Because the decoder is fully structured. It actually looks at everything that gets from the encoder and try to make some sense out of it. And this is not doable. Like we don't have any structural assumption over the decoder in order to make sense of it. So it took some time to understand, and then, as usual as we do in deep learning, we think about the most reasonable heuristic. And we said, okay, we have the best assignment from the first part of the gradient. Let's just plug it into the decoder and leaving one dimension free. And then take the maximal assignment of the decoder perturb information, and let's hope for the best. So it's actually somehow smiling and not really clear that this will work out. And actually, we were sure it will not work out. But surprisingly, it did work out, okay, which is good. So although Gumbel softmax and all these counterparts using the full information all the time seamlessly, when we do this approximation, which is still not clear to us how good it is, like at least it works in practice, although slower. But this is, again, not why we went towards a high dimension, because we actually want to look at structured encoders. We want to understand how can we make connections between, okay, smiling and with glasses, smiling without glasses. Like learning these relations in a way will help us to generate images in a better way. So we're working with a spin glass model, structured prediction, like we have many names for it, structured encoders where we account for pairwise interactions between 2 variables. Basically, we cannot use Gumbel softmax anymore because making the softmax over a structured encoder will be exponential. We actually need to only look at the Argmax. And so luckily for Argmax, we can use efficient solvers. So we have the Cplex or Gurobi, which are very efficient. And when we have some structural restrictions over the pairwise features there, like supermodularity, which for those of you who remember the time, it says that two attributes prefer to be in the same position. So a person prefers to be smiling and with glasses, and then it's somehow more plausible to it. And then we can use max flow algorithms to get efficiently the Argmax. Yeah.
What is the choice of a prior then? Like if you now have pairwise interactions in Latin space?
The prior is it's a uniform prior. It's fully decomposable, and yet we have problems there because the K divergence need to be approximated. Yeah, so we use the mean field, but it's like, and that's I guess the main problem in this direction. Yet, this funny thing is, for those of you who worked on structures and variational encoders, and we have Ivan Titov work on perturbation powers, and we have the program generating work that I currently forgot the authors, but all of them shut down the KL divergence. You can see, and they actually write it like implicitly in the paper. There is something weird happening with the KL divergence. Everybody only look at the reconstruction error, and I don't know why the KL divergence only interferes. It's really not clear to me yet what's going on there. So you can see, we can, in order to be efficient, we can work with Cplex, it gets the best results. We can work with max flow, it has similar results, but extremely faster. And we can work with the unstructured, just ignoring the structure completely, it works worse and faster. So basically we have some options, and I think exploring structures it's still not yet not fully understood. It will be nice to understand when we can deploy this max flow to be, on the one hand, efficient, on the other hand, have meaningful interactions between pairwise variables. So now I'll start you know what, let's do it this way. Questions? Yeah. We have in the reinforcement paper, we have a comparison. We have this variance reduction built-in, inherently built-in. So the variance is lower than reinforce. We saw that. There is something we're still missing. Reinforce can work with the advantage or value in a way to reduce the variance in a way. And we still don't understand how well it compares to it. So we have some work to understand that. It's not clear yet. More questions? So these are the most important things that I want to convey. Like we have data understanding, which is the encoder, reasoning, which is the discrete space that can be structured or unstructured, and then decision, which is the decoder in this case. And now I'll just present few things in the 5 to 10 minutes that I'll take to myself around this just presentation. So it works in semi-supervised learning. We took the setting of Max again, and it works nicely. It's not surprising it works in semi-supervised because this work is somehow related, actually very well related to direct loss minimization that we worked on. And adding loss function, it's natural in this case. And we also apply this thing in reinforcement learning, which is nice. What we did effectively is worked with A-star sampling. And we worked with the machinery that, after understanding our machinery and the field, we also saw Wouter, I hope I pronounce it well, and Herke, I know, I hope I pronounce it well, and Max, have the similar thoughts about the Topcase sampling. And what's happening here, it's extremely cool property of the Gumbels. You can set the max value and be very fluid with the Argmax value. You say, oh no, the Argmax value should be this. Oh, it should be that. So we can do it in many places. So we do it here in order to create a search heuristic that I'll show in the next slide. We can do it, well, we didn't do it. Sontag and Oberst did it in ICML as well, in causality. Right? So just changing the policy, what would have happened if we'd done this? And this is exactly, they use the same idea. This statistical independence between max and Argmax is extremely important. So what we are doing in this work, we are trying to explore trajectories. So we find the best trajectory. Like if you remember, the gradient is the difference between two trajectories. The best trajectory, and then the decoder perturb trajectory, or in this case, reward perturb trajectory. So we can go down the tree to find the best trajectory easily without actually expanding everything. And we can start going from a priority queue over this trajectory, start taking elements in order to expand it to get the second gradient, right? The perturb gradient with the reward. And then we don't need to explore the whole tree the same way was done in this lab, that for top K got only K samples. For us, in the gradient estimation, we only take priorities from the heap and just explore the trajectory from the heap itself, so we don't need to explore the whole search space. Our main motivation is that when we do reinforcement learning and we choose a trajectory, we want to backtrack not a single step, but we want to backtrack a lot. Well, and this is exactly what happens here, because the first leaves have higher priority, so you can go back again easily, and unlike reinforce when you only accumulate all the time. Some questions?
What are the different colors in this?
Well, the blue is the decoder plus perturbation, or here is the policy plus perturbation, it's the same thing. And the brown is when you add the decoder or the reward, it's the same thing. Right? The expected utility that you want to get. Okay? So for one gradient, we need only the blue, and the second gradient, we need only the brown, and we want to explore this space in a very efficient way. So we want to not generate the full tree, but only a heap and just choose what's best at the time. More questions? Yeah, 5 minutes. Oh. I'll be done even before. Another thing, and this is actually a perfect fit for the top K, we are struggling with it. We just published something in TACL. We try to do the top K in the learning phase. We are still failing on it. What we are doing, we are learning, and it's the same motivation, right? We are learning some representation over the connection graph of the sentence, and then we sample K best parses, and then we take the probability, or we count how many times an edge appeared in the K-based parses, and on top of that we do maximum spanning tree. So this is the decisioning space. The problem here is that we didn't find yet a good way to propagate gradients through the whole process. We will try to do this thing maybe, I don't know if it will work. So what we did, we just resorted to the old type of learning. We did learning trees at the first phase, and then we sampled in our backyard, and then we came back with all the trees that we sampled, summed everything up, and went again to the lab to run another learning phase. And what we've seen here, which is important, is that we need to learn the variance of the perturbation. It's as important as learning the mean of the perturbation. And this is something that we are working on recently. If you think, it's the same with variational dropout in a way, or Bayesian neural network. You learn twice as much parameters. You learn mean and you learn variance independently of each other, right? You don't want to tie both of them. And it's extremely important to learn the variance because it says how much a specific edge is certain about its position. What we learned is and what we are trying to do now is a bit step away from Gumbel. Learning the variance in Gumbel is learning the temperature of the Gibbs distribution. We are trying to step away from Gumbels and go back to Gaussians, not because it makes any difference, because we believe that this behavior is more general than the Gumbels. Although the Gumbels are the only distribution that gives you the independence between max and argmax, I agree. I'm not sure that on the practical side it makes much of a difference, pretty much because we've seen that the distribution looks pretty much the same and everything is approximate. And anyway, I want to understand better the connections between the exponential family distributions. In this respect, it's the Gaussians and the Gumbels. What we've seen from this is that walking over dependency trees, when we walk over dependency trees, when you have graphs with cycles, it's no longer that the Gumbel-Argmax and the Gibbs distribution are the same distributions, right? So we did the top K of Gibbs distribution, which is easy to get. There are some works of Yair Weiss on it. And we did the top K with the Gumbel distribution, the Gumbel-Argmax. And we've seen that the K-best is not really informative. And this is something was presented also was noticed by Ben Tasker at the time of doing the terminal point processes. There is not much diversity in the Gibbs distribution because it only tweaks a variable here and there, while the Gumbel-Argmax, since it employs optimization, it really picks different modes of the probability. So we get more informative, we get better quality, dependency paths with better quality, and we get somehow diversity, and we don't really know how to measure diversity. But what we've seen is that MFN is multiplicative noise that we add, and AFN, where we control the variance, and AFN is only mean, that we don't control the variance there, it's a unit variance. And then there we see that we can actually have like the whole quantile in a way in the perturbation space. In the K-best, we only in about the 0.6, 0.5, 0.7. Like it seems to be better diverse in a way. We also see it in trees, but it's still not fleshed out. So basically, as I said, I'm thinking about learning now in 3 phases. Data encoding reasoning, which I think the most exciting, how machine is reasoning about a problem, how a person reasons about a problem, how we connect both entities, and then the decisioning. Another thing that interests me in this respect is attention models. It's pretty much the same thing. Although I do emphasize I'm thinking about attention models differently than they are described in the literature. I'm thinking about a probability distribution that is placed on top of data instead of some summarization of the data. And we can see it's the same thing. We have a data processing that which is taking, say, an image and running through VGG, or taking a sentence running through LSTM, and then we create probability distributions on top of the image and the sentence in order to correlate them. And we do that for visual question answering. And you can see that this correlation is extremely important. We can see that we can actually, a question and visual attention can direct, say, the person that needs to make sure that the system works well to the right places. You can see if I'm asking about the animal, it looks at the animal. If I'm asking about the plastic container, it looks at the plastic container. I truly hope this will be effective in medical, actually, more than sheep and goats, because I think doctors will need that in the future. Thank you.
Questions?
So maybe we can start off with like the analytic gradient and all possible latent variables, and then the repermutation, right? And we've looked a lot at the bias, which haven't said so much about the variance of things, right? Which of course is 0 for this for the empirical risk, right? Do you think that could explain some of the learning results, like kind of the plateaus you saw in the data? Or?
Yeah, that's a good question. It might be. I'm still puzzled by it. I don't really know. Yeah, I'm trying to, I don't know. That's a good question.
Just the kind of additional stochasticity might help you get out.
Maybe, maybe. I think, but I don't even know how to, so I'm trying to quantize this intuition in a way, but I don't even know like how to start. I think I think this is my intuition and motivation, but I don't really manage to grasp fully because it's very non-convex. I don't really know how to approach it. But this is what I see from the results, which is quite surprising.
So thanks for a great talk. So so Gumbel-Argmax starts to horribly fail if you have to do many of them in a sequence because this by is somehow compound and it makes things bad. So if you want to train a deep neural net with discrete latent variables, and you have to constantly do Gumbel-Argmax, it will hurt very soon, right? So is this expected to do better in that respect?
Well, I'm biased, right? As my gradients. Yeah, of course. I want to try that, and I think so, I hope so, actually. And the question is how to make this decision as a structured space that goes to all layers in the same time, or do it sequentially. I don't know yet. It's a good question. There are some explorations we need to do in this respect.
But you're focusing on sort of an encoder decoder. But I'm just doing a deep neural net with discrete latent variables, right? So it's a somewhat different setup.
So I would do everything instantaneously, right? I would do all discrete choices at once. This is for now how I think about it. I would have all the information that I can get, make all the discrete choices, even if weights didn't change, get a gradient for that. Just do another pass of continuous gradient or something like that. But I would work with structured setting over the whole network. It makes more sense to me now, but it's something that needs to be explored.
But what if you can't do that? What if you have to make the discrete choices as you go?
That's a good question. So you need to hold some things. Maybe you need to only do parts of the gradients, right? You need to see where the parameters lie, and maybe you need to. So another thing that you can do, I'll show you. Here it is. It might be the case that theta decomposes. It can go with every dimension. Right? Not theta, sorry, epsilon. We can have different epsilon to different dimension. And this is what we actually used. We didn't find a good theoretical explanation, but it gave actually better results. If epsilon goes to different directions, so you can make updates only to parts of the network at a time, because you can control the rate of the epsilon. In a way, you give high epsilon to part of the network that will not influence the gradient, low epsilon to places that will influence the gradient significantly. So if you can control parts of the network, it might help to do it sequentially.
All right, we've got time for one more short question, if there is one. All right, let's thank Tamir again.